We're going to start now. Um, in the last class, we talked about potential difference and potential. So we defined potential difference as the work done per unit charge in moving a charge from one point to another point. So specifically, what we said was that potential difference, as denoted by VAB, which we could write as the difference in potentials at point B and at point A. This is so if we were to put Q here, then what this integral would give us is the work done by an external agent in moving the charge Q from point A to point B. And now if we talk about work done per unit charge by bringing that Q to the left-hand side, then what we get here is the potential difference between points A and point B. And we also saw in the last class that potential at a point due to a point charge equals Q divided by 4 pi epsilon naught R. Now, and this in this definition, what we're assuming is that there is a reference point. So when we define our potential, there's always a reference point, and the reference point, we take it as infinity. And at that reference point, the potential is zero. So when we talk about potential at any point, it is always with reference to something. It's relative to something, and the reference point is infinity. So the potential at any point B can be defined as at B is the work done per unit positive charge in moving the charge from, so we normally say from A to B, but when we talk about potential difference or work done from A to B, but if we're talking about just potential, not difference, then it is the work done in moving the charge from the reference point to the point where we are measuring the potential. And the reference point is infinity. So in moving the charge from infinity to B, and at B, that is where we are measuring the potential. So we could write VB as, so work done in bringing the charge to point B from infinity. So the point A is now infinity. And when this infinity is the reference point at which the potential is zero. In the last class, we also talked about a special derivative, a vector derivative of a scalar field, scalar function. We talked about the gradient. That special derivative is gradient. So gradient of potential field. So we'll continue talking about that today. Potential gradient. What we saw in the last class is that electric field intensity is given by the negative gradient of the potential field. Electric field intensity, as we know, it's a vector quantity, and V is a scalar quantity. But once you take the gradient of any scalar quantity, it becomes a vector. Now, today we'll start by talking about the direction of this gradient. And to talk about that, we will imagine free space first, where we'll think about a surface at which the potential value is fixed everywhere. So let's say there is a surface where potential does not change. Its value is fixed at any point on that surface. And so that I can draw this easily, I'll just draw a plane on XY. Not a plane, but a surface like that. Let's say it's right on the XY plane. And so on this surface, potential is fixed. So anywhere on this surface, if we measure the potential, its value does not change. So let's assume that. And such a surface is called equipotential surface. Okay, so potential is equal everywhere. And let's say we are at point, we'll call this point 0. And we consider a small displacement. Okay, small displacement, and so that we reach point 1. From point 0, we are now getting to point 1. And this small incremental displacement, we will call that dl. So what we know is that we know V equals minus E dot dl. Or if we're talking about incremental voltage potential, we can say dV equals minus E dot dl. And for any dot product, we can write it as the product of the magnitudes of the vectors involved times the cosine of the angle between them. So let's say E without the arrow is the magnitude of E. So we have the magnitude of E, and then dl without the arrow would be the magnitude of dl. And then we have the cosine of the angle between them. Let's say the angle is alpha. And so when we are moving from point 0 to point 1 on this equipotential surface, then the potential does not change when we move from 0 to 1. The potential difference is 0. So moving a charge from point 0 to point 1 would not require any energy, because the potential difference between point 0 and point 1 is 0. So we can say dV equals 0. In other words, we have minus E dl cosine alpha. So if the left-hand side is 0, so this also has to be 0. And electric field intensity, the magnitude, let's say, is not 0. And similarly, dl is also a non-zero quantity. So to make this product equal to 0, we must have cosine alpha equals 0, right? That means alpha must be 90 degrees. That means on this equipotential surface, the electric field intensity has to be perpendicular to that displacement that we are considering. And the displacement is within that surface. What we are trying to do here is find the direction of the electric field intensity. How is it related to the potential field? That's what we'd like to find out. And now what we can tell so far is that when we move from point 0 to point 1, the potential difference is 0. So that means electric field intensity must have a 90-degree angle with that DL path that we have taken. And there are so many directions that we can make, and it can be perpendicular with DL, right? We can choose a line like that. We can choose a line like this. And this is 3D. So there are many other possible vectors that will have a 90-degree angle with this DL. But what we're going to do next is consider some other point on the same equipotential surface. Let's say this is point 2. And so that we have a different DL this time. And again, for this case also, if we evaluate potential difference, dV equals minus E times dL cosine alpha, that is still 0. So that means alpha is again 90 degrees. No matter what displacement we choose on this equipotential surface, E will always be at 90 degrees angle with the displacement. So which means that any line we pick on this equipotential surface, the electric field intensity has to be at a 90-degree angle with that line. So that means there are only two possibilities for the electric field intensity. It has to be either along the positive z-axis or along the negative z-axis. Okay, so the electric field intensity has to be perpendicular to this entire surface. That means perpendicular to this entire xy plane. So that means either in the AZ direction or in the negative AZ direction. So from our analysis, what we can tell is that electric field intensity is perpendicular to the equipotential surface. And this is always true. We're talking about electric field intensity and potential fields, but if we consider any scalar field and we find its gradient, the gradient is going to be a vector and its direction is always going to be normal to the surface where the scalar field is constant. Okay. Any question? All right, that's one important point to remember. Electric field intensity is normal to the surface where potential is constant. Now, what we're going to do next is the final topic in this chapter is energy energy in the electric field. From previous classes, what we know is that if there is an electric field in space and if we try to bring a charge in that field, that charge is going to experience some force. So it will take some energy to bring a charge in a field where there is non-zero electric field intensity. Now, the question that we're asking in this final topic is, what is the energy stored in any electric field? And to answer that, what we'll consider is first a free space where there are finite number of point charges, so discrete charges. What will be the energy associated with that field? And then we'll also talk about the energy when there are different continuous charge distributions, line charge, volume charge, and surface charge. So we'll start with energy in presence of discrete charges. So imagine free space. And let's say in this free space, in this volume, we are bringing in several charges from infinity. To bring a charge from infinity to any region, we need energy. So let's say we bring from infinity charge 1 and we place it at point 1. Then we bring another charge, Q2, and we place it at point 2. Then we have Q3. So we continue in this manner until we get to, let's say, Qn. So there are n discrete charges. And to bring each charge from infinity to a region where there is non-zero electric field, the external agent will have to expend some energy, and that energy will be stored in this region. So in the very beginning, we are bringing Q1. And before we bring in Q1 from infinity, there is nothing in free space, right? So if there is nothing in free space, there is no electric field. That means no energy will be required to bring Q1 from infinity to point 1. So Q1, no energy needed. But after Q1, we bring in Q2. When we bring in Q2, if Q1 is already there, it is already creating an electric field. So now to bring Q2 from infinity to point 2, that will require some energy and or work done will be non-zero, and we can write that as so work done in placing Q2 at point 2. This is a simple derivation. You just need to understand how we get the final result. To bring Q2 at point 2, so what will be the work done? We know that the work done will be equal to Q2, the charge that we are bringing from infinity, times the potential at point 2 due to the charge 1. And we'll write it in this way. So what this notation means is potential at 2 due to charge Q1. So we'll use this notation. All right, that's it for charge Q2. And we are going to also call this W2. W2 equals that. And similarly, now I'm going to copy this. Then we bring in, after bringing in Q2, we'll bring in Q3. So let me change this to Q3. Work done in placing Q3 at point 3. We'll call that work done W3. So what is that work done? Since we are bringing in Q3, it will be Q3 times the potential at point 3 due to the charge Q1. Okay, the charge Q1 will be exerting some force at this point, so we have to take that into account. Similarly, there is also charge 2 already present, so that will also exert some force. So energy has to be expended to account for that as well, and that will be equal to Q3 times V32. The first one is due to the charge at 1. The second one is due to the charge at point 2. So we can keep going like that. Let's write one more. Now, if we consider charge 4, work done in placing Q4 at point 4, that will be equal to Q4 V for 1. This is due to the charge at 1. Then Q4 V for 2. And Q4 V43, and so on. Now, what would be the total energy in or the total work done or total energy expended? We'll call that WE, and that will be equal to the sum of all, which will be Q2 V21 plus Q3 V31 plus Q3 V32 and then all of this. So we are adding them up to find the total energy that we have to spend to bring all the charges to this free space. And for each term we have in that sum, what we can notice is that if we expand any term, for example, let's try expanding this term. What that means is, so we have Q3 and then V31, as we know, potential field due to a point charge, that we can write as Q1 divided by 4 pi epsilon naught and the distance between 1 and 3, right? So now what we can do is we can switch the order of 1 and 3. So we have Q1, Q3 divided by 4 pi epsilon naught, and we can also write R13 as R31. And if we write it in that way, we could rewrite it as Q1 V13. So that you can notice the symmetry here. Q3 V31 is also equal to Q1 V13. So we can rewrite every term in this expression for WE in the different order. So the first term, we'll write it as Q1 V12. Similarly, second term, we'll write it as Q1 V13 plus Q2 V23 plus Q1 V14 plus Q2 V24, and so on. What we did here is we wrote two equivalent expressions for the total work done in bringing all the charges. And now we are going to add the two expressions we have. So if we add the left-hand sides, we get twice WE. And if we add the right-hand side, we'll get terms like this. We'll have Q1 and then V21 plus V23 Q1 V31 plus Q1 V41, and so on. If we have n charges total, it goes up to n1. Similarly, we have Q2 and then V12 plus Q2 V32 plus Q2 V42, and so on. And finally, what we can do is we can factor out Q1, right? In the top expression, we can factor out the charge Q1 and the remaining potential, the sum of the potentials, V21, V31, V41 up to Vn1. What that now represents is, this is, the very first term is the potential at point 1 due to charge 2. The second term is the potential at point 1 due to charge 3. And the third, and after that, potential at point 1 due to charge 4, and so on. So every term there is the potential at point 1 due to different charges. So if we add them all together, we can write it as the total potential at point 1. And if we do that for the other terms as well, so we can write it as Q2 V2 plus Q3 V3 and so on. It goes up to Qn Vn. So finally, in the compact form, what we can write is that the twice of the total work done is equal to m equals 1 to n Qm Vm. Yeah. Yeah. So one more thing. What we are interested in is the total energy. So We equals half. So if there is free space and there are many discrete charges, a finite number of discrete charges, then the total energy in that field, in that electric field, is equal to half of the sum of these products. And these are for discrete charges. Now, if we have continuous charges, then what happens? So if we have a line charge, what happens is the summation becomes, first of all, integral. And we have to replace Q by the line charge density, and then we have to integrate that. So the expression becomes We equals half of rho L, and then we have voltage field, potential field, and then dl. Similarly, if we have a surface charge in free space, then We equals half of surface charge density times potential and surface integral. Similarly, if we have a volume charge density, then We becomes half of this volume triple integral, rho V, and then we have potential. So note that we are using lowercase v for volume and then uppercase V for potential. Yeah. No. The surface could be anything. And also voltage could be a function of x, y, z, and ds will also be functions of x, y, z. Now, one final thing we're going to do is for a volume charge density, we're going to derive an alternative expression for We. So what we have is We equals, this is a useful expression, but we're going to find an alternative expression as well. So using vector calculus, we'll use an identity, and that identity is so if we're taking just like in basic calculus, if we're taking the derivative of a product, then we can apply the product rule. The scalar field, when we take the derivative, it becomes this, right? Gradient. And then if we have a vector field, we know that its derivative that we've already seen is, we can apply the product rule by incorporating all these three terms. And what we can do is we can replace rho V by del dot D. Right? This is something that we know from chapter 3. And also what we know from chapter 3 is that we can replace a surface integral by a volume integral. So what we saw in chapter 3 is so d dot ds equals, this is a surface integral, it's a double integral, but it can be replaced by a volume integral, which is a triple integral. Del dot d dv, right? So applying all these and also noting that d equals epsilon naught e. So what we can write is we equals half of volume integral, and then we will have d dot e. So we have electric flux density, and then we have electric field intensity. And where replacing d by epsilon naught e, we can write it in terms of the dot products between just electric field intensity. And the good thing about this alternative expression is that now we can just consider the magnitude of the electric field. If we have E dot E, it can be written as magnitude of electric field intensity squared. So a simplified formula for WE that we'll often use is half. We can bring out that epsilon naught and volume E squared dV. So an alternative expression that we'll often use is this.
The extra E from the second detail from delta from divergence of the field to diverge to detail times.
So there's also, so I didn't do the full derivation here. We also have this V term, right? 1D comes from the rho V equals del dot D, but then we also have V, the scalar field. So when we apply the product rule, we end up with this term also, gradient of the potential field, which we know to be electric field.
On the second line, closed surface integral, that's not the same thing as the work integral. You were just showing what you proved in the previous chapter.
Yeah. This one is just what we did in the previous chapter. That's right. The expression that we want to focus on is this one. Okay, so if we know the electric field intensity in any region, then we can compute the energy stored in that field. Right, and as an example, what we'll do is we'll look at the problem. See if I can find problem set 4. From problem set 4, let's look at problem 16A. So what is given is V equals 200. The potential field in free space is given. It is 200 divided by R, and it's in volts. And what it's saying is find the energy stored in free space for the region. The region is given to be 2 millimeters R to 3 millimeters. And then theta varies from 0 to 90 degrees. Phi varies also from 0 to 90 degrees. Now, what is the energy stored in free space? So what we derived previously is that if we know the electric field intensity, we can find the energy stored in that field, right? But what is given to us right now is the potential field. So can we use that formula? All that we know is this, right? But the formula that we have is over here. Can we still use that formula? Can we get E if we have V? Yeah, how do we get that? Gradient, that's right. That's what you did in the last class also, right? So what we know is that electric field intensity is given by the negative gradient of V. And this field, scalar field, is given in the spherical coordinate system. So for the gradient, now we're going to have to use the formula for the spherical coordinate system. So in your formula sheet, so in your formula sheet on page 2, towards the bottom, you'll see the expression for del V, and that is partial derivative with respect to R, AR. And there's also derivative with respect to theta, derivative with respect to phi, but we don't need to write all that, right? Because what we see is for the given V, it is only a function of R. So when we take the derivative with respect to theta or phi, it's going to be 0. So let's not write all that. We just need this term. That is the electric field intensity. And now we plug in 200 divided by R, AR. Negative 200, and then, so derivative of 1 by R would be minus 1 by R square. So 200 by R square AR, volts per meter, is the electric field intensity. So that is the total electric field intensity. All we need is the magnitude. So magnitude equals 200 divided by R square. Right, so what we need for that formula is, now we have that. So applying the formula, WE equals epsilon naught divided by 2. And we now need volume integral of E square, right? So 200 square divided by R to the 4th. And then we have dV. How do we do this volume integral? Well, R varies from, so it's given, the range of R is given 2 to 3. It's given in millimeters, so it becomes 0.002 to 0.003. Then theta varies from 0 to 90 degrees. And phi also varies from 0 to 90 degrees. Then we can factor out 200 squared. We are integrating this. And the expression for dV is, for the spherical coordinate system, we have R squared sine theta dr d theta d phi. Any question? So this way, if an electric field intensity or potential field in any region is given, we can evaluate the total energy stored in that field. And I'm not going to complete that. I'll make this a classwork problem for today. Just find the value for that. We have low attendance. Do you have any exam tomorrow?
Yes.
For what?
Signal system.
And remember, you have to convert you might need to convert the angles to radians. I'll write the options. Anyone got an answer? Any question about this? Did you get one of the numbers here? Okay. Which one did you get? All right. Then let's move on. Now let's go look at where we are in this course. So some content from the very first lecture in this course. So I answered the question, what we are learning in this course. So we're learning electromagnetics, which means electricity and magnetism. And why we study them together, like I said in the first class, because these two phenomena are fundamentally connected. The magnetic phenomena arise from electric charges in motion, and changing magnetic effects can produce electric currents. And that is why we study them together. And this course is divided into first static fields and time varying fields. So everything that we've been learning in this course is static fields. And static fields is further, static means fields are not changing. So electric field intensity, electric flux density, potential field, these are all fields or functions in simple words, right? So we're talking about fields that are not changing with time. We haven't even concerned ourselves with time at all, right? Everything is fixed. They don't change with time. In all our expressions, we have X, Y, Z, but no time. Everything is static. And static fields is further divided into two categories. One is electrostatics, where we just learn about electricity, electric field intensity, electric flux density, potential field. And that's in chapters 1 to 6. So we did chapters 1, 2, 3, 4. We're going to skip chapters 5 and 6 for now. We need some, just a few things from chapters 5 and 6. And as we need them, we'll get them from chapters 5 and 6. What we're going to do next is magnetostatics. So we're going to now learn about magnetic fields, but still they are not going to change with time. They are going to be fixed in time. And that's chapters 7 and 8. And once we're done with electrostatics and magnetostatics, we'll bring them together. As we bring them together, we are going to get time varying fields. And that's in chapters 9 to 14, but we won't be able to cover all chapters, just a couple of chapters. So we are going to start magnetostatics, chapter 7. And also, I mentioned in the first class that all fundamental laws of electromagnetics are summarized by four equations, and they are known as Maxwell's equations. And there are two ways to write those equations. One is what we call differential or point form, and the other one is called integral form. And of the four equations that describe the entire electromagnetics, we have covered one. So these two equations that we saw in chapter 3, they are actually one of the four Maxwell's equations. Okay, so this is where we are. And now we are going to begin magnetostatics, chapter 7. And this chapter is called Steady Magnetic Field. So when we learned about electric fields, electrostatics, the first law that we learned was Coulomb's law, right? Because the Coulomb's law described the force experienced by one charge due to the presence of some other charge. In other words, this is what we had. Force experienced by charge 2 due to charge 1, Q2, Q1 divided by 4 pi epsilon naught R12 square. That is how we started. our electrostatics. And this is Coulomb's law. We could also write it in terms of electric field intensity at point 2. And we could write it as E2 equals Q1 divided by 4 pi epsilon naught R12 square AR12. The force and electric field intensity are closely related because they are just, they are related by a scalar charge. So that is basically Coulomb's law, the very fundamental law for electrostatics. There is a similar law for magnetostatics as well, and that is known as Biot-Savart law. That's our starting point. And just like Coulomb's law, this is also an experimental law that describes magnetic field intensity. We had electric field intensity to quantify, to characterize an electric field. It tells us what the strength of an electric field is and what its direction is, in what direction it is going to exert force on any charge. Similarly, to characterize a magnetic field, we have a vector field, vector function known as magnetic field intensity. And this law describes a certain type of magnetic field intensity due to a certain type of current. So imagine a very small incremental length conductor. Let's say its length is dl, and it is carrying current I. And any current carrying conductor will have magnetic field around it. And the current that we are talking about right now, it is a direct current. Okay, it is constant. Now, this current will have a magnetic field around it, and we are interested in finding the magnetic field intensity at point, let's say, point 2. We can call this P2. So what we're gonna do is we're going to draw this line, this vector. We'll call this R12. Let's say the source, the current, is at point P1. What Biot-Savart law says is that the differential magnetic field intensity due to this differential current element okay, that is given by, so before I write down the expression, magnetic field intensity, we denote that by H, and it's a vector field, so we have an arrow. And now right now we're talking about differential magnetic field intensity, so we'll also have D. This DH will depend on the length of that current carrying conductor. It depends on the magnitude of the current. It depends on the distance. It's inversely proportional to the square of the distance between the current and the point where we're measuring the magnetic field intensity. And it also depends on the angle between the DL and the line R12. So it is equal to the current, that displacement, differential length, dl, it will have a certain direction, 4 pi epsilon naught R12 square. And notice the similarity between this magnetic field intensity and the electric field intensity as given by Coulomb's law. So Biot-Savart law is just like the Coulomb's law, but for magnetostatics, right? So they both have this AR12, this unit vector. They both have the same denominator. And the source for the electric field is Q1, the charge. The source for the magnetic field is this current, direct current. And there is also this, we have cross product here instead of simple vector AR12. So what is the direction of this magnetic field intensity? So there are the cross product, we can use the right hand rule. So if we represent dl, the length, by our thumb, and then the AR12 by our index finger, and then magnetic field intensity would be given by the middle finger, right? Because that would be true for any cross product. There is another way to get the direction of the magnetic field intensity. So again, using the right hand, if we hold our hand fingers like this, if the thumb is pointing towards the direction of the current, then the fingers curl towards the direction of the magnetic field intensity. Okay, so the curling of the fingers, that direction is the magnetic field intensity, whereas the thumb points in the direction of the current. Does that make sense? All right. So if that makes sense, here is one problem. So I don't have the handout for you yet, but you just need this figure. So there are several configurations given, several pairs of current and magnetic field intensity. Which one of them, which ones are correct? So based on what I described. So remember, if we hold our right hand like this, the fingers curl in the direction of the magnetic field intensity, and the current points in, thumb points in the direction of the current. And one new notation here is that, so if you have a circle with dot, that means it's a vector going, it's a vector coming out of the paper, coming out of the screen. So it's the front view of an arrow. Okay, so this is out of the screen towards us. And then if you have this cross, that means into the screen. So that's the back view of an arrow. So into the screen, away from us. Okay, so let's look at each figure and determine whether it's this figure is accurate or not. The first one, is that accurate? This one you have to think in this way. What do you think? Right? What about the second one? Second one is just the opposite of the first one, right? So this has to be wrong. So why don't you look at the rest of the figures, and so we'll call this classwork 2. Write the numbers that are correct. So we'll write 1, comma, what else will go on that list? Did everyone find this?
I guess so. I think it's
Exactly, yeah.
Might be a loss. We have those. How do you know when it's? It just. Because if you can have this, it's
Yeah, hold on a second. All right, what did you get? 1 and 1 and 4, that's it? And 7. All right, any question?
I just